supposed to do it, Dad. They want us to do it this
I don't
way.
know that way. Why would they change math? Math is math.
okay,
Math
Dad.
is math.
G'day nerds, welcome back to McGrathematics for another episode in the Extension 2 saga. Starting off with a flashback from the 2017 HSC exam. We've got complex numbers chosen so that these complex numbers form the vertices of a regular polygon as shown. Which polynomial equation has all of these complex numbers as its roots? Pause the video and decide on whether you're going for A, B, C or D before I go through my solution and see if we get the same answer. Okay, here we go. So we've got 8 equally spaced roots around the complex plane. We can see 8 vertices of our octagon. This means they must be the 8th roots of unity, okay? Because they're all equally spaced, they all have a length of 1. They're going to be the 8th roots of unity. That means they are the solutions to this equation. Complex number to the power of 8 equal to 1. This is covered in the previous video to this, which is called roots of complex numbers. Okay, so if z to the power of 8 is equal to 1, it means that z to the power of 8 minus 1 is equal to 0, which is similar to option C. So if you said option C, you are correct and you got 1 mark in this HSC multiple choice question. Okay, on to today's video, which is all about curves and regions in the complex plane. This video is about a year overdue because all of these diagrams and animations took me absolutely forever. So if you find this lesson useful, consider subscribing if you're not already, and maybe share this video with a friend of yours who is lucky enough to be studying Extension 2 Maths this year. All right, let's get right into it because this might be a big one. All right, starting off with the concept of what a locus is. So in mathematics, a locus is essentially a path of a particle, or a point, sorry, under some direction, which is given by an equation, okay? Basically, an equation gives you a path, that path turns into a picture, okay? So when you think of locus, think of just an equation determining the path or the shape or the trajectory of a set of points which form a line or a curve. That's the quick version. Let's start off with a point that's moving through the complex plane such that it is always 3 units away from the origin. So picture in your head what that might look like. If you're thinking of a circle, you are correct. Here is a point moving around the complex plane. So the distance to the center is always 3 units, making this circle. Okay, we know from our knowledge of nonlinear functions that this circle's equation is given by x squared plus y squared equals 9. So this equation is the locus of the point given by these conditions. Okay, so that's our equation, aka locus. Now we can rearrange this expression by taking the square root of both sides to say the square root of x squared plus y squared is equal to the square root of 9. And now the square root of x squared plus y squared can also be written in complex numbers as the modulus of a complex number. Okay, so we may have thought of this curve in terms of x squared plus y squared equals 9 previously. Now using our knowledge of complex numbers, we can also describe this as modulus of z equal to 3. Okay, so the picture of this equation is a circle. Okay, so modulus of z equal to a number is going to be represented graphically by a circle in the complex plane with a radius of a, because we are always a units from the center of the complex plane. If we want to shift the center around, we just need to do z minus a complex number, which gives us the coordinate of the new center, which looks like this. Okay, so x plus iy is our center, a is our radius, and there we have our circle. Basically, we're saying the distance between z, which is the blue line, okay, the distance from z to this point is equal to this number, okay? Interpreted graphically, we get a circle. So first example, we've got sketch the locus of z defined by z plus 3 minus 3i, the modulus of the whole thing, is equal to 3. Okay, so to sketch this, we're going to make it look more like this equation here, where we have the modulus of z take away a complex number. So inside our modulus, we'll factor the negative out of this complex number to make it look like this. Okay, we have z minus 3 plus 3i. If we expanded out these brackets, we would get what we started with right here. So we can look at this and interpret it as, all right, the distance from z to this complex number is always equal to 3. That tells us we have a circle where this complex number is going to be the coordinate of our center, and the radius is going to be equal to 3. So we look like this. Center it here, and radius of 3 looks like this. Ta-da! Okay, now we have our picture. Part B is find the minimum and maximum values of modulus z and argument z. So think of z as it can be any point along this circle. We're going to think about what point on the circle has the biggest and largest distance from the center. That's what the modulus is. And we'll think about which points have the smallest and largest angles measured from the positive real axis. Okay, so argument is the angle of the point from the real axis. So starting off with the distance, the shortest point is going to be right here. That's the closest point to the center right there. So we'll have to figure out this length. And then the furthest point away is going to be across the other side of the circle over here. Okay, so let's do some working out. So we'll start with the argument apparently and say that, all right, so the smallest argument is going to be right here. At this point right here is a rotation of 90 degrees from the real axis. So that's our smallest argument, pi on 2, 90 degrees. The furthest point in terms of rotation is over here. Okay, right here, this point, this blue point on the circle has rotated 180 degrees from the positive real axis. So if we were measuring this angle, we will get 180 degrees, which is pi. Okay, so there's the minimum value of the argument of any point on this circle, and there's the maximum value of the argument of any point on this circle. Now for the modulus, we're going to need to find the length of this red line, which is the radius of the circle plus this red bit here. We can achieve this by just finding the modulus of the center of the circle by doing a bit of Pythagoras to find the length of that red line. So we'll do 3 squared plus 3 squared is equal to 9 plus 9, which is 18. So using Pythagoras, the length of this red line is the square root of 9 plus 9, which is 18. So if this red line is equal to root 18, and we know that the distance from the center to the edge of the circle is of course the radius, which is always 3, we can say this point right here, this length right here is going to be root 18, take away 3, leaving us that part right there. Okay, so root 18 we can also write as 3 root 2 to be a little bit more simplified. And say, all right, so the smallest point right here is 3 root 2, take away the 3, leaving us with that part here. If we want the modulus of the point across the circle, we'll do the red length, which is root 18, and then we'll add the radius, which is 3, and then we get this point here, which is the furthest point from the center. Okay, so there is our smallest value of mod z, and there is the largest value. So that's the first point is this distance here. The second expression is from here all the way out to here. So again, these are much easier to explain on a whiteboard. It's a bit hard with PowerPoint, but I'm just kind of doing my best today. Hopefully you understand what I'm saying. If not, I don't know, send me an email, who cares? This is free. You get what you pay for. All right, some more examples. Sketch the locus defined by the following. So when you have some inequalities involved, you're going to be looking at, instead of a line, you'll be having a region. We want to sketch all the points on this Argand diagram where the modulus of z is less than 1. That means we need to include any point where the distance to the center is less than 1. So we have a circle. The outline of the circle is the points where the modulus is equal to 1, which we don't want to include. That's why it's got a dotted line. And we're going to shade the inside of the circle. Everything in this blue region right here is less than 1 unit to the center, so the modulus is less than 1. Okay, so you're essentially going to be sketching z equal to 1, and then you're determining whether you're inside or outside, and you're going to think about whether your border is going to be dotted to not include, or if it's going to be filled in to include when you have a greater than or equal to. Okay, over here we have the distance of any point from the point I is going to be greater than 2. So we'll start off by sketching the circle z minus I equal to 2. So there's our center at I. Our radius is 2. Okay, and we want to include every single point where the distance from the point to I is bigger than 2. That means we're going to be outside the circle, so we're sketching everywhere outside the circle. Everywhere inside is less than 2 units to the point I. Everywhere outside is greater than or equal to 2 units from I. And again, because this time it was a greater than or equal to instead of just a greater than, our region, which is the edge of the disk, the circumference, this is included, and that's why it's got a full blue line. Okay, now for a couple more. This time we have the modulus of z plus 1 is greater than 1, but less than or equal to 3. Okay, first thing we need to think is that when we're trying to think of in terms of regions, it's always easier if what's inside your modulus is in terms of a minus rather than a plus. What I mean is here, this reads as the distance from z to I. Okay, so it's easier to read if you have a minus inside your modulus. So first thing I'm going to do here is, instead of writing z plus 1, I'm going to write z minus negative 1. Okay, what this means is our distance from the point -1 needs to be greater than 1, but less than or equal to 3. So I'm going to put a dot at -1 as our center. We're going to draw a disk where we have a radius of 1 unit, and another disk where the radius is 3 units. Now we're shading the this disk here, which is in math is called an annulus, would you believe? Because everywhere inside here is is less than 1 unit away from the point, but we want to be greater than 1 unit away. Everywhere outside the blue ring is going to be greater than 3 units away, but we want to be less than or equal to 3 units away. Okay, so when we have a double inequality, what we're going to see is an annulus where we're between these two values. Okay, the inside circle is dotted because we have a less than here. The outside circle is full because we have a less than or equal to. Okay, so seeing something like this, you can expect to draw a disk or an annulus, whatever you want to call it, you freaks. Okay, for part D, we have the real part of z is greater than or equal to 1. Now remember, in terms of complex numbers, the real part is just the x value. So this is really just saying, sketch the region x greater than or equal to 1. So we'll draw a line at x equals 1, okay, 1 on the real axis, and now we want everything to be greater than or equal to 1. So we want everything over here. Okay, here is our region, including the boundary where the real part is greater than or equal to 1. All right, beautiful. Let's do some more hectic ones. We've got double moduli now. A bit of fun. Okay, this one is saying the distance from z to I is equal to the distance from z to -3i. Again, we're going to write this plus as a minus minus because you need to have a minus in here. So it's distance from here to here. So we want all the points where the distance from I is equal to the distance from -3i. So we're going to put a point at I, which is right there. We're going to put a point at -3i, which is just here. And now we want to have every single point which is equidistant from these 2 points. So we could be right here, we could be right here, we could be right here. When you're going to be equidistant from 2 points, the locus of that is going to give you a straight line. Okay, this straight line here is perfectly equidistant between these 2 points. Okay, so a double moduli is usually going to give you a straight line. Over here, same thing, we have a double moduli, so we'll start off by writing everything in terms of minus. So we'll have z minus the point 2 minus I. Modulus is equal to z minus 4 plus I. So now we read this and we interpret it as, okay, we need to be equidistant from 2 minus I and 4 plus I. So we're going to put a dot at 2 minus I right here. We're going to put a dot at 4 plus I, which is just here. And now we need to draw a line that is exactly halfway between these 2 points. So the way you do that is you pick the point halfway between them, and then you draw a line perpendicular to the line between your 2 points. Okay, so we're going to be going like this. Okay, this point here is equidistant, and this line is perpendicular to the line from this point to this point. Okay, so if you needed to find this equation, you could find that midpoint, you could find this gradient, find the perpendicular gradient, and then you'll have your equation. But that's how we interpret it graphically, by writing in the correct way and knowing what we're looking for. So yeah, a lot of content knowledge in this lesson. It does take a while to get good at reading the questions and knowing what you're expecting to see. So yeah, lots of practice recommended because there's always usually a few marks in the HSC just on sketching locus, typically about 3, maybe 4 marks. So yeah, don't skip this one. Okay, and our last one for this section is z plus z conjugate is equal to the imaginary part of z. So with the examples so far, I kind of had a rough idea of what the picture looked like just by looking at the equation and just making some interpretations. Sometimes there will be equations like this where I look at it and I don't know what it looks like. So if you look at the equation, you're like, I don't know what that looks like, you go to plan B, and plan B is to get some algebra involved. So we are going to write this equation instead of in terms of z's, we are going to write it in terms of x's and y's. So we have the value of z, we're going to write that as x plus iy. The value of z conjugate, we're going to write that as x minus iy. Okay, and the right hand side is the imaginary part of the number, which is the coefficient of the I, which is y. Okay, this is the exact same statement as the question, except instead of z's, we've got some x's and y's involved, so we can make an equation to give us an idea of what it looks like. Okay, this one's not too bad because the iy and the negative iy cancel out. X plus x is 2x, so we have the line y equals 2x, and suddenly I don't know what that looks like, but I do know what y equals 2x looks like. It's a line with a gradient of 2 passing through the origin. So there is our locus. Okay, so yeah, if you look at the question, you're not sure where to start, plan B is to write in terms of x and y and go from there. Okay, another one we've got, again, I'm looking at this, it looks complicated, I don't know what it looks like, so I'm going to write things in terms of x and y and see where I get. Left-hand side is modulus squared, right-hand side is z plus conjugate plus 3. So let's write everything in terms of x and y. We've got the modulus right here, but we're squaring it. We've got z, z conjugate, and the constant on the end. Okay, the square root and the squared cancel out. On the right, the iy and the negative iy cancel out. So we end up with x squared plus y squared on the left equal to 2x plus 3 on the right. So I've got an x squared and a y squared, so I know it's going to look like a circle. I don't know exactly what it looks like yet. I'm going to have to do a bit more algebra. So I'm going to bring the 2x across the left-hand side to become a negative 2x. And now I'm going to complete the square on the left-hand side because we're trying to find the center and the radius of this circle. So I've got x squared minus 2x. So I'm going to complete the square by adding a 1 to both sides because now we have a perfect square here. Don't forget the plus 1 on the right, so the 3 becomes a 4. And now factorizing this, we can write this as x minus 1 all squared. And now suddenly I can look at this and finally I can say, all right, sweet, I know what this looks like. It's a circle. The center is at 1, 0, and the radius is 2. So I can do my center at 1, 0, and I can do a circle with a radius of 2 units. And there you go. There is the locus of this equation. All right, beautiful. That was fun. Let's move on to some argument restrictions. So that section was all about looking at modulus. This section is now looking at argument, which is also equally likely to be asked of you in your HSC. Okay, first one, we are going to sketch every single point where the argument of the complex number is equal to minus pi on 3. So every single point where the angle of rotation from the real axis is negative 60 degrees. Not to scale, but looks roughly like this. Okay, we've got a vector going from the center all the way out to the edge, and we've got an angle of rotation of pi on 3 in the negative direction. I forgot to add it in, but when you do these, it's good practice to do a hollow circle at the origin because we are not including the origin in our line. Just everywhere on the line, not including the origin. So yeah, if I was a better maths teacher, there would be a white dot there to show we don't want to include the origin because you can't have an argument from the origin. Doesn't make sense. Okay, over here, we are reading this as, all right, cool, the argument from the point 2 is equal to pi on 4. So it's a similar idea over here, except we're being shifted 2 units to the right. So instead of starting at the origin, we're starting at 2. Again, there should be a hollow dot there, but I'm bad at my job. From that point 2, we're drawing every single point where the angle of rotation is pi on 4, which is 45 degrees in the positive direction. So we've got an angle of pi on 4 there, starting at the complex number 2, and there is our picture for that equation. Let's do some more. All right, we've got some inequalities involved. So we're gonna have some regions, so some more fun sketching for me. We want to sketch all the arguments that are between negative pi on 2 and pi on 6. Okay, so negative pi on 2 goes straight down, dotted line because we have a less than, so it's not included. Pi on 6 is 30 degrees in the positive direction, which is up here. This time it's a full line because we are including it. Again, should be a hollow dot there. I'm sorry, please don't dislike this video. I'm trying my best. And we want to have every single point that's between here and here. So we're doing a bit of sketching, which means a bit of word art for me. And there we go. There is our region. Every single point in this blue region has an argument that's greater than pi on 2, not including, and less than or equal to pi on 6. So there we go. Isn't that fun? All right, bit of a hectic one over here. We've got the argument of z, but we've taken the absolute value of it is less than pi on 4. Okay, so the size of the argument when you take the positive or negative value is pi on 4. And also, the value of the modulus is less than 3. So there's a fair bit going on here. This is a typical HSC style question. They like to combine two things into one picture to really test you out. Okay, so our argument could be pi on 4, or it could be negative pi on 4, because we're taking the absolute value and making it positive again. Okay, so anywhere in this region here, if we found the argument and made it positive, it would be less than or equal to pi on 4. But we also want the modulus, which is the distance from the center, to be less than 3 units. So we're going to need a circle with a radius of 3. Again, it's dotted because we have a less than, not a less than or equal to. And we're sketching the overlap. We want to be inside this circle, but also between these two vectors. So we're going to be just sketching this sector right here. And that blue part there is your region, where you're between these two arguments, but you're also less than 3 units from the center. All right, cool little Pac-Man. Let's keep going. Okay, moving on to some more hectic argument restrictions. Disclaimers for this section. These questions are really hard to explain with a screen and a mouse, but I'm going to do my best. I'm going to do a brisk explanation of these questions because a full explanation would add another 5-6 minutes to this video, and I like to keep them as quick and brisk as possible. Also, questions in these form have not been in the HSC exam for the last 15 years as of 2022, which is why I don't do a lot of these types of examples, but I thought just in case. I'm not saying these won't be in your exam, I'm just saying I think it's very unlikely based on recent history. Anyway, the first one, the argument of z from 2 divided by z minus minus 2 is equal to pi on 2. I'll show you the picture and then I'll try and explain to you what it means. It's going to be an arc of a circle where one of the endpoints is 2 and the other endpoint is negative 2. And for this one, the arc of a circle is going to be a semicircle. Okay, the reason that is we are plotting every single point where the argument from 2 and the argument from negative 2 meets at a point that is a right angle, which is pi on 2 degrees. Okay, if you don't know much circle geometry, the angle inside a semicircle is always going to be 90 degrees, and that's why these two vectors meeting at a 90 degree angle, tracing around this point makes a semicircle. Okay, that's the quick version. The top number is one of your endpoints, and the bottom number, which is really a minus 2, so think of that as z minus minus 2 over here. Those are the two endpoints of your arc, and the arc traced out has to make these two lines joining to make an angle of pi on 2. It's super confusing. If you want a more in-depth explanation, probably ask your teacher because, I didn't want to go down a 10-minute rabbit hole about argument laws and, vectors and stuff. There's the short version. This one over here, again, we're going to be tracing out the arc of a circle. Endpoints are still 2 and minus 2. However, this time, they're making an angle of pi on 3. Okay, so if you think about vectors from here and here meeting at an angle of pi on 3, it's going to give you more of a circle, which is why we have more of an arc. Okay, so obviously these are hard to draw, which is why I don't think they're very regularly assessed, but they are in the syllabus, so I have to briefly gloss over them. But yeah, when you see them in this form, think to yourself, all right, I'm going to be drawing an arc of a circle. If it's 9 degrees, it's a semicircle. If it's less than 9 degrees, it's going to be more than a semicircle. And if it's less than 9 degrees, you're going to be having a smaller arc. Okay, that's the quick version. Sorry, I'm moving on. These ones are a bit more common and they're similar style. This one is saying the difference between the arguments from 2 and minus 2 is equal to 0. Again, let's draw the picture and then I'll explain to you why it looks like this. So one point is going to be, I finally used a hollow circle. One of the endpoints is at 2. The other endpoint will be at 2i on the imaginary axis. And now we're going to have two vectors and they're going in opposite directions. Okay, the reason for this is the dumb way of thinking about it is you have two vectors that are meeting at an angle of 0, which means they aren't meeting, so they're going in opposite directions. But the real reason is if you took any point on this blue line up here, say this blue point here, the argument from this point would be this angle right here. Okay, that would be the argument. The argument from this point down here would be the same angle. Okay, so look at where my mouse is tracing. From this point, the argument is this angle here. From this point, the argument is this angle. And because those two angles are the same thing, when you subtract them, you get an answer of 0. Same thing down here. Any of these points on this blue line have the same angle of rotation from here or from here. Okay, so you have the same argument from both points. When you subtract them, you equal to 0. But again, the way my dumb brain remembers it is you've got 2 points meeting at an angle of 0, so they're going in opposite directions. Again, it works. Over here, similar idea. We have one endpoint being 2 and the other endpoint being 2i on the imaginary axis. This time, we have two vectors that are meeting at an angle of pi, which means they're going together, and you have the inside of this line segment. Okay, again, the real explanation is if you found the argument of any point on this blue line, so from this dot, it's going to be this angle here. From this dot, it's the angle here. If you subtracted them, you would end up with an answer of pi. Okay, so when you see it in this form, so the short version is when they look like, let's go back for a sec. When they look like this, where you have angles, you're going to be having arcs of a circle. When the answer is 0 or pi, instead of a circle, you have either straight lines going in opposite directions or straight lines meeting together. Okay, so there was one multiple choice question like this a few years ago, but other than that, questions like the last two slides are very, very rarely assessed. I'm just covering them so I don't get sued. But yeah, again, like I said, you get what you pay for at McGrath-Mathematics. Okay, moving on to some further examples and some challenges. We are going to find the ranges of modulus z and argument z for this locus determined here. Okay, so we have the modulus of z from a number equal to a number. So like earlier in the lesson, this is going to give us the equation of a circle. So we can make it look a little bit nicer by taking the minus outside of the complex number inside the modulus. So we read this as the distance from z to 4 plus 4i is equal to 2 root 2. So we have a circle where the center is 4 plus 4i, so 4, 4, and the radius is 2 root 2. So to fit this on here, I'm going to have to make every gap on this axis equal to 2 units instead of 1 unit. We have a circle with a radius of 2 root 2, which looks roughly like this, not to scale, don't sue me. And the center is at 4, 4. So again, these gaps are 2, so that's 4, and that's 4. Now, like before, we're trying to find the biggest and smallest distance from the center, and we're going to try and find the biggest and smallest angle from the positive real axis. So, starting off with the distance from the center. So again, we're going to find the length of this red line, like we did earlier, by doing a cheeky bit of Pythagoras. So we've got 4 squared plus 4 squared, and then we're going to do the square root to find the length of that dotted red line. That's equal to the square root of 32, so that's the red line length, which is equal to 4 root 2, bit of fun. Now to find the smallest point, we're going to take the length of that red line, and we're going to take away the radius of the circle, which is 2 root 2. To find the point furthest away, like before, we'll take the length of the red line, and we're going to add 2 root 2. Okay, that's going to come later. For now, we're going to turn this red line into a triangle, because we need to find some angles to find the lengths, find the limits of our argument. So this circle is looking like this, all right? It's right angled because, fun fact, whenever a tangent meets a radius, they always meet at right angles, which is a bit of circle geometry for you. We've got 4 root 2 here, which we figured out from the Pythagoras over here. We know this red line is 2 root 2. And so because we've got 4 root 2 and 2 root 2 here, this kind of looks like the triangle that you would have seen in the trigonometry section of the advanced course, where you have 1, 2, and then root 3 here. Okay, except we've scaled it up. Instead of 1, we've got 1 lot of 2 root 2, and on the hypotenuse, we've got 2 lots of 2 root 2. Or if you just do a cheeky little bit of trigonometry, you'll get that the angle over here, which is just here on the picture, is equal to 30 degrees. Okay, so that's pi on 6. So now we have all the pieces we need to put this together. So I'm just going to put that picture over there, because we still need it. So for our modulus, like I said, the smallest length, this part right here, this is the length of the red line, which is 4 root 2. Take away the length of the radius, which is 2 root 2. And the furthest point away on the other end of the circle is the red line of 4 root 2 plus the radius of 2 root 2. So that gets us 2 root 2 on the left and 6 root 2 on the right. And those are the ranges of our modulus. Okay, so all the points in this circle are going to be within these two distances from the center of the diagram. Now, for the angle, we know that because this is 4 and 4, this is an isosceles triangle here, which means this. So it means the argument of this dotted red line is going to be 45 degrees. We're trying to find this angle in here because that's the smallest possible argument, and then we're trying to find the angle over to this point. Okay. So what we're going to do is we're going to take pi on 4, which is this angle right here. We're going to take away the angle inside the triangle, which is 30 degrees, aka pi on 6. Then for the other end, we're going to take the 45 degrees right here, and we're going to add the 30 degrees to get up here. Okay, so the smallest argument is right here, which is 45 take away 30, and the largest argument over here is 45 plus 30. And that gets us the range of our argument. It's going to be between 15 degrees and some other number. Hang on, let me math this. 45 plus 30 is 75, okay? That should be 5 pi on 12, not 5 on 12. Should I edit that out? Oh, probably not gonna. Anyway, pi on 12 and 5 pi on 12 are the two ranges of your argument. All right, I think I need a nap. Let's move on to some HSC questions to finish off. We've got, from the 2014, band 4. These questions are usually around band 3 or 4 because once you've done a bit of practice, you see the patterns and you know how to sketch the pictures. So we've got two restrictions. We've got the first one is the modulus of z is less than or equal to the modulus of z minus 2, but also the angle of z is between minus pi on 4 and pi on 4. Okay, so straight away, this becomes a bit easier when you think of the left-hand side as z minus 0. Okay, we're saying to ourselves, the distance from 0 is less than or equal to the distance from 2. So we're going to draw the arguments first. We've got minus pi on 4 down here, and we've got pi on 4 up here. Okay, we need to be within these two arguments, or within this triangle inside these two vectors. However, there is the line x equals 1. Why do we care about that? Because it is exactly halfway between 0 and 2. Remember, the way we're interpreting this is we need to be closer to 0 than we are to 2, because the distance from 0 needs to be less than or equal to the distance from 2. So that means that we need to be closer to 0 than we are to 2. So we need to be to the left of this line so that we're closer to 0. If we're to the right of this line, we're closer to 2. So we're to the left of this line, we're between these two vectors, which means we're in this little triangle. Oh, no, go back. We're in this little triangle just here. Okay, within the two arguments and closer to 0 than we are to 2. Okay, beautiful. And finishing this absolute mess off with a band 6 from 2011. We're sketching the diagram of modulus of 1 plus 1 on z, less than or equal to 1 for 2 marks. Okay, this is a band 6 because it requires a bit of algebra manipulation and a bit of clever rearrangement, because looking at this picture, I don't know what it looks like. All right, I don't know what 1 plus 1 over z looks like. Don't know what the modulus looks like. So remember from earlier, I said when you don't know what it looks like, you go to plan B. Plan B is to go back to x's and y's. So first thing we'll do is we'll write 1 as z over z, and we'll write 1 over z as 1 over z because we're going to combine these two fractions. Okay, so combining everything inside the modulus, we get z plus 1 over z. My computer's lagging a little bit, but we'll make it through. Okay, now we can split these two moduli apart and say we've got the modulus of z plus 1 divided by the modulus of z. Now this is good because we know that the modulus of z is a distance, which means it's a positive number, so we can multiply it across the right-hand side, and we don't have to worry about this inequality turning around because we're definitely not multiplying by a negative number, because how can a distance be a negative number? That's not how distances work. So multiply it across, and we're looking like this. Okay, now we're going to get our good friends x and y involved. So we're going to write the left-hand side as z as x plus iy. I've written the plus 1 here because 1 is a real number, so I'm putting the real bits together and the imaginary parts together. Over on the right-hand side, we have the modulus of z, which is x plus iy modulus. Okay, now modulus is you take the real part, you square it, you take the imaginary part, you square it, and you take the square root. Same thing over here, real part squared plus imaginary part squared, square root. Okay, because everything's positive, we can just square both sides and we don't have to worry about the inequality again. So we square both sides to get rid of the square root, and we have x plus 1 squared plus y squared less than x squared plus y squared. We can subtract the y squareds from both sides, so they're gone away. And while we're at it, we may as well expand this binomial product here and write it as x squared plus 2x plus 1 less than or equal to x squared. Okay, now we can subtract x squared from both sides, and we get 2x plus 1 is less than 0. We'll put the plus 1 across the right-hand side to make it a negative 1. Divide both sides by 2, and all we need to sketch is that the real part, x, is less than or equal to negative a half, which is not too challenging. Get up a picture right here. Okay, here's the real part at negative a half. We want our real part to be less than negative a half, so we're everywhere on the left, and so there is our blue region. Okay, so knowing to split it up like this and then get x's and y's involved, following the algebra gets you to a very simple sketch, but not many people thought to do this, which is why it was a band 6 question in 2011. Okay, and that's the end. Thank Christ for that. A bit of a mess, but like I said, hard to do with the PowerPoint, but I did my best. Hopefully you got some value from that, and if you're looking for more practice questions, here's what I recommend to my classes, but you do what you want to do. Thank you so much for watching. That's probably my last video for the year, but I'll be back next year with some fresh content for Advanced, Extension 1, Standard 2, and Extension 2 Maths. So stay tuned and subscribe if you want to see it in your feed. All right, thanks very much. Happy New Year when it gets to there, and yeah, all the best. See you in the next video. Bye for now.